Hello, everyone. Today we are going to move to chapter 4, and chapter 4 is going to be about general vector spaces. As you remember, in chapter 3 we had Euclidean vector spaces, and they were basically similar to what we have like in school, like 2D vector space, 3D vector space. That's a vector space which is around us, which is describing like space around us. General vector spaces are going to deal with more extended vectors, a little bit more complicated, a little bit more unusual. We're going to start with section 1, real vector spaces, and we are going to go over axioms of real vector spaces. For Euclidean vector spaces, actually we can prove all these axioms just using component representation of vectors. But for real vector spaces, we are going to set up these rules as axioms, the stuff which we are not proving but actually using to verify if something is a vector space or not a vector space. Let's start with definition of vector space. Yes, I usually like to write down on the board myself, but in this case, because there's so much writing, I decided to concentrate on talking and kind of copy the picture somewhere online. So what is a vector space? As you remember, for two three-dimensional vector spaces, we have vector addition. We can add two vectors, right? We also can multiply a vector by a scalar, and we also had an operation which was a dot product. Here, guys, we are going to talk about only two operations, operation of addition of two vectors and operation of multiplication of a vector by a scalar. So let's read the definition. So let's V be a set on which two operations, vector addition and scalar multiplication, are defined. We are going to talk about dot product a little bit later, and that's going to be a kind of extra, which is going to be defined slightly different vector spaces. So there are like 10 axioms which are supposed to be true for like any objects from this set V on which you perform next operations, vector addition and scalar multiplication. So for all next axioms, U, V, and W are going to be vectors which belong to vector space. They are not necessarily supposed to be actually vectors. They can be some other objects. It's going to be important that objects follow the axioms. And we can also have some scalars, and scalars are C and D here, where the scalars are belonging to real numbers. Okay, so let's start with first axiom. First axiom is closure under addition. Well, what does it mean? If you take two vectors from that set and you add them and the result belongs to the set again, that means that the space is closed under addition. Sometimes you define a set and you perform operation and the result goes outside of like set, which is going to be like violation of the first axiom, closure under addition, and that's not going to be a vector space anymore. Next one is commutative property. We would like vectors to commutate, which means that like we are restricting a little bit like how vectors can behave, but this is going to be a very useful property for us. Next one, associative property, that we can move parentheses whichever way you like when we have a addition of three vectors. It's not important how we move parentheses. Very good associative property. Additive identity. It looks like we are talking about one, right? Usually we are talking about identity, we are talking about one. But if you recall, like what was identity matrix or like what we use as identity, that's actually something which does not change the property of the object. Or like here, if the identity for addition is actually going to be not one, but zero. And look what this identity is doing. You add it to any vector and you get the vector back. So we are going to have zero vector, and it's going to be called additive identity. Next one, additive inverse. Well, usually we know inverse for multiplication, right? Inverse for multiplication is like, for example, 1/3 is inverse of 3. But here we need inverse for addition. Well, we remember that whenever you have inverse and direct vector or object, You add them together and you get this 0, additive identity. If you apply to multiplication, it's going to be like multiplying, right? And 1 here. But for addition, our identity is 0. And we do have inverse, and inverse is going to be denoted by negative u, which does not mean that it's actually going to be something really negative. It's just, we're going to define it later, like what is negative, but it's supposed to be some object from the very same set, which you add to your like original object, and they make 0. And it's not necessary that 0 is actually 0. Next, 5 axioms are going to be about scalar multiplication. So first 5 axioms were about addition, and this like next 5 axioms are going to be about scalar multiplication. So first, scalar multiplications not supposed to bring the object outside of the set. So if you take object multiplied by some number like 5 or like any real number, the resulting object is not supposed to go outside of the set. It's still supposed to belong to the set. Distributive property. If you take a number and multiply it by sum, you can actually multiply this number by each object and add them together, and you're still going to get the same result. If you have two numbers, just real numbers, C and D, like 5 and -7, for example, and you add them and multiply by an object, it's going to give you the same result if you just take each number, multiply by that object, and add them after. So this is kind of two ways to do distributive property, 2 vectors and 2 real numbers. Associative property. Look, we had associative property for vector addition. Here we have associative property for scalar multiplication. So if you multiply 2 numbers by a vector, it does not matter like how you set up parentheses. Either you multiply number by product of number by vector, or you just can multiply numbers and then multiply the result by vector. And the last property, very important one, is scalar identity. We had additive identity and it was 0, right? Scalar identity means that if you multiply number 1, no, like from real life, multiply number 1 by any number, you're still going to get the same number. Here, guys, if you multiply number 1 by any object, you're still going to have the same object. So one object is actually the same object, called scalar identity. I'm going to consider example, which is not going to be our regular addition scalar multiplication, which we used for normal vectors. If you recall, like for Euclidean vector spaces, like 2-dimensional vectors, 3-dimensional vectors, all these properties are working just because we literally can check them by plugging in components, right? And everything is working. I'm going to consider example of slightly more complicated vector space, which is still going to be vector space, but very, very unusual. Okay, so I'm going to move up, and what is going to be next? I'm going to consider example of vector space. That's going to be my first example. This example is going to consist out of next like operations. And by the way, I did not tell you something. And in this like notation, in this like picture, they don't tell it. But actually, this addition is a special vector addition. It's not necessarily supposed to be our regular addition as we understand it. So I'm going to circle it everywhere. So sometimes it's going to be just a normal addition, but in some cases, it's going to be something very, very different. So addition operation is going to be defined, like what you consider addition. So everywhere here, addition is like not a regular addition, probably. Probably it's a regular addition, but probably it's not. Also, scalar multiplication, they do not write down anything here between the scalar and the vector u. I'm going to rewrite it, and I'm going to write it now like scalar, and I'm going to put multiplication, and then I'm going to put vector u. Also, this not necessarily is going to be our multiplication as we understand it. And that's what I'm going to consider in the next example. So guys, let's consider a vector space of vectors, which are going to be just real numbers. u and v are going to be just any real numbers greater than 0. So both are going to be greater than 0. So let's consider real numbers greater than 0. Are they going to make a vector space? I'm going to define addition as product of these two numbers. So to do this vector space addition between these two numbers, it's going to be just a product of them. I'm going to show example. For example, if you have like two numbers, number u equals 2, for example, and number v equals 3, vector addition of them is going to be product of 2 by 3, and that's going to be equal to 6, not like 5, as we expect 2 plus 3. So, well, again, this is our choice of the operation. We are going to name multiplication addition. Why not? Second, scalar multiplication as, give me a second. I'm going to use letter K for a scalar. K, scalar multiplication by u. So here K is a real number, and this is a vector from this vector space. And it's also a real number, just these real numbers can be only positive. These real numbers can be anything, positive, negative, or 0. So, only positive. And this one, any real number. You see the difference? This is just a real number. This is object of a vector space. So how do I define this multiplication? Of course, expect something tricky from me. I'm going to define as u to the power of k. Let me show you how it's going to work as example. So for example, my k equals 2, my u equals 3. So what is going to be k multiplied by u? Well, normally, guys, it's supposed to be like 2 multiplied by 3 equals 6, right? But because my definition is slightly different, that's raising to the power, that's going to be 3 to the power of 2, which is going to be actually 9. You see? Well, this is just an extreme example to show you like that addition and multiplication can be really anything. And here, you see, it changed. Instead of addition, we use multiplication. Instead of multiplication, we use raising to the power. Okay, now let's check how axioms are going to work here. I'm going to start with axiom 1, 2, 3, and then just go like over each axiom. I know that's going to be a little bit boring, but you know, if you see it once, you probably are going to remember it much, much longer. So guys, if you have a number u greater than 0 and number v greater than 0, then what is going to be u plus v? Sorry, I'm going to uh, just write down u. So, well, u plus v, special addition, is going to be product of u and v. If each of them is greater than 0, then the result is greater than 0, which means that it still belongs to real vectors greater than 0. So the first axiom works. It's closed under addition. If, for example, you multiply u and v and get a negative number, then it's a real number. But because we defined our space as numbers greater than 0, it's not greater than 0. So it's not in space, and that's going to be violation of the axiom. Here, axiom is working. Okay, axiom number 2, commutative addition. Well, here everything is going to be simple just because we are dealing with normal multiplication. So u plus v is going to be what? U multiplied by v, right? And because this is just normal multiplication between numbers, we can exchange them vu, and then we can write it down v, sorry, trying to write down plus, but somehow made it. So kind of works. Number 3, associative law. U plus V plus W. And we can put parentheses as we like. So let's put parentheses like this. And what it's going to be? Well, you know that U addition is multiplication of number U by the product of V by W, right? And we know that for regular multiplication, so this one is kind of unknown operation, or like the operation we define. This one is just regular multiplication, regular, just like 2 multiplied by 3 is equal to 6. So here I can change position of parentheses. I know that from algebra, I can put parentheses like this, and it's still going to work, right? But according to my definition, this product is actually addition of vectors u and v, and then addition of vector w. So the rule number 3 or axiom number 3 is working. Number 4. So number 4 is talking about 0. What is going to be 0 here? Remember, what is 0? U plus, sorry, my writing is so bad. Let me kind of fix it. U plus 0 supposed to be still equal to u. Is it going to be? Well, because it's multiplication, we need to know by what we multiply u to get u. Well, kind of obvious that this question mark is actually equals to 1, right? If we multiply a number by 1, we are still going to get the same number. So actually 0 for this vector space is equal number 1. Well, so still kind of it works, and we are going to be happy about this. Number 5, what is going to be inverse? Remember that's supposed to be like minus u, which you add and get 0. Again, it's not regular 0, it's this 0. 0, which we kind of found like in fourth axiom. Well, let me write it down. Like, imagine that we have number u, and we multiply it, addition is multiplication, by something, and we get our 0, which is actually 1, right? So by what we need to multiply u to get 1? We need to multiply it by regular multiplication by 1 over u, right? So that 1 over u is going to work as inverse. I'm going to write down that inverse is going to be 1 over u. It's going to be literally number. So if somebody gives you number 3, the inverse of that number 3 is going to be 1 over 3. Sounds a little bit crazy, but well, that's how the space is built. Okay, so we checked first 5 axioms. We do have inverse, we do have everything. By the way, can we kind of find inverses to all elements? Yes, because if you look at original definition, we consider only elements greater than 0. So we don't have 0 in our vector space. So we don't need to worry about like what is going to be inverse of 0. There is no 0 in this vector space. So real number 0 is not included here. Okay. So let's move to multiplication axioms, scalar multiplication axioms. So we are going to start with our first multiplication of a scalar by vector u, right? Which is supposed to bring us back into that vector space. What is going to be multiplication? That's number to the power of k. If this is greater than 0, any power of number greater than 0 is going to be greater than 0, and it's going to be a real number. So it's closed under scalar multiplication. It still returns us a number which belongs to positive real numbers. Like no matter which number you raise to the any power, if the number is positive, it's going to return us positive number. Okay, number 7. Number 7 is distributive law over addition. So we have k, this strange cross multiplication, and u then plus v. How it's going to work? Well, let's just kind of plug everything in using our rules. So I'm going to start with parentheses first and then apply this. So addition is going to be just a product of u and v, right? Scalar multiplication is raising this product to the power. Now, guys, we use regular algebra laws. If you raise a product to the power, it's like you raise the first number to that power and the second number to the power, then multiply them, which is going to be exactly what? This one, uk, it's actually k cross u. This multiplication is actually addition, and this one is k cross v. Okay, so we kind of did a distributive law. Distributive law works. Yes, number 8. We have just 3 more. Now, okay, let's do distributive law for numbers. You guys, here we do have that special multiplication next to u. Let me do it one more time. So I put it in circle, but this plus is not in circle. That's just regular addition of two real numbers. Like, for example, 2 plus 3 is going to be 5. It's not going to be like 6 or whatever. So this is just regular multiplication. So I'm not circling it. So let's see how it's going to work, like on numbers. So we have u to the power of k plus m, and that's just a regular multiplication. We remember that add of the powers can be represented as a product of numbers raised to this power, the same base, right? And what is this? This is k multiplication of u. This is addition. And then k multiplication of v. So it looks like we distribute, oh, not k, m. Sorry. M, and that was actually 2. Well, which is going to be like distributive law for this, right? Okay, because we kind of distributed this parenthesis u multiplied by k and u multiplied by m and then addition. You see that this regular addition, regular 2 plus 3, is turning into unregular addition, which is 2 to the power of 3, which is 9, not 6. Okay, 9. Shifted the whole thing a little bit this way so I can have more space. Axiom number 9 is going to be double product, right? That associative law for multiplication. K, sorry, K multiplication M. I'm sorry, here's supposed to be the strange multiplication. K cross. So what I do, I multiplied my vector by scalar m, and then result is going to be a vector, and I multiplied by scalar k again. What I'm going to have in my special case. So this product m by u is supposed to be u to the power of m, right? If you multiply the result by k, it's going to be raised to the power of k. We know that we raise power to the power, it's just a product of powers. And if we go back to our definitions, we are going to have m multiplied by k. I would write down better k multiplied by m to keep it like in order, okay? I'm sorry. For multiplication over here, it's not important. And this special multiplication by u. You see that we can put parentheses this way or this way, doesn't matter. Here, by the way, normal multiplication, like 3 multiplied by 2 is 6. It's not 9. Here is vector multiplication. Okay, so we checked 9, and the last one to check is 10. And what is going to happen if we check 10? 10 is the last one. we need to check that we have scalar identity, right? Remember that scalar 1 multiplied by scalar multiplication by u must be equal to vector u, scalar identity. Well, let's check if it's going to actually work. I don't think that we need to invent here anything. So this multiplication means that 1 scalar multiplication by u, it's u to the power of 1. Well, we know that any positive number to the power of 1, it's a number itself. So checks. So we checked all 10 axioms. And all of them are working, and we're supposed to happily say, good, this is a vector space. Our vectors are just real numbers. They're not really vectors. I use it as example first, that operations not necessarily supposed to be operations are not necessarily supposed to be really addition and multiplication. Second, vectors are not necessarily supposed to be actually vectors. They can be something else, some other objects. Now, I'm going to give you a couple of more examples of, somehow my computer is kind of doing everything by itself. More examples of vector spaces, and I'm not going to check all axioms on them. So I'm going to give you vector space of real valued functions. Let me use a different color. Okay. So example number 2, vector space of real valued functions. Well, kind of functions. Just any functions you know from calculus. So we're going to define addition of two functions as just a sum of the functions, just regular sum of two functions. Just instead of like one number, you are going to have a third function, right? If you have one function, another function, and the result is going to be a third function. You just add them functions together. Multiplication by a scalar is going to be just multiplication, regular multiplication of function by that number, which is kind of, remember, we are scaling, we call it scaling. Okay, well, I don't want to check axioms here, but you can try to do it, and you are going to see that, well, the sum of any two functions is still a function, right? And if you multiply a function by any number, it's still a function, so it's closed under addition and scalar multiplication, and you can check the rest. For example, what is going to be actually zero here? That's going to be a zero function. Zero function is just a constant zero. So I'm going to write it down that zero vector here is going to be just zero function, like f of x equals zero, a constant function. It's not going to be just one zero, it's going to be lots of zeros actually. Well, that's just like an example. Let's consider some examples of non-vector space, okay? Just to make sure that you understand that not like all possible kind of sets are working as vector spaces. So example number 3, not a vector space. Let's consider next. Something happened to my screen. Cannot move, scroll it up. Oh, now I can. So I'm going to consider R2 vectors u and v, which belongs to two-dimensional vectors. And I'm going to set up addition as u plus v, just regular addition, like by components. I'm going to write down u1 plus v1, u2 plus v2. So two-dimensional vectors uv, they have components u1 v1 and u2 v2, and to add them, you just add components. Multiplication. K u. I'm going to make it slightly different from normal multiplication. I'm going to multiply k by the first component and put 0 instead of second component. It's going to be a multiplication. And this one is not going to work as a vector space. And if you start checking the axioms from the first, number one, number two, you're going to see that this surprisingly strange vector multiplication and addition is going to pass all 9 axioms. You're going to start like, what is going to happen if I add these two vectors? Well, all addition axioms are going to work just because this is just regular vector addition, and we know that it's going to kind of satisfy all the rules of vector addition. Scalar multiplication is not very different from scalar multiplication. Regularly, guys, how do we multiply by a scalar? We multiply first component by that scalar, second component. The only difference here is 0 over here, right? And actually, scalar multiplication is not going to bring vector outside of the space. It's still like if you substitute the last component with 0, it's still going to be inside of that space, right? Just the last component is 0. The only one axiom which is not gonna work if you just start checking all of them, it's going to be axiom number 10. I'm going to start checking axiom number 10. So 1 multiplied by vector u supposed to be vector u. So what if I do this multiplication as 1, I'm going to use this special multiplication. Multiplied by vector u is going to produce what? 1 multiplied by u1 and 0. And you see that it's not equal to vector u, which is actually u1, u2, right? The components of it. Well, unless it's already 0 here, not for all of them, right? It's supposed to work for all of them, all vectors u. And it's going to work only for those vector u which have 0 as a second component. You see? So axiom does not work, so it's not a vector space. Do you need to check all axioms to verify that's not a vector space? Well, if somebody is asking you to find all axioms which are not working, yes. But if somebody is asking, show that this is not a vector space, well, you will need to find the axiom which does not work. And kind of, lots of axioms are going to just work. You will need to kind of have a feeling like, oh, this axiom is not working. Okay, I think I'm going to stop this and make it a first part and then move to the second part. Second part is going to be kind of theorem, which I'm going to consider, and I want to separately give it as a separate video. Okay, so let's stop at this point and then do the second part separately.